Okay, so we'll see now some more examples for solving recurrence relations. We'll see first the linear format one, and then we'll do the other format. So let us say you're given x of n equals x of n minus 1 plus phi for n greater than 1. That's recurrence relation, and the basic condition for this is, you can call this basic also as terminating condition, and that is more appropriate to understand recurrence, because this is like how long this recurrence will be true, and that's the terminating condition. Because when I say x of n equals x of n minus 1 plus phi, there's no right straightforward answer for what is x of n. You have to compute x of n minus 1, and then x of n minus 1, there is no straightforward answer. You have to compute x of n minus 2 and so on. That's what we also saw in the factorial problem as well as the other one. So the terminating condition of writing m of 0 equals 0, or whatever the number of bits of for 1 is 1, and in this case x of 1 equals 0. The terminating condition gives you a straightforward answer, and we kind of build back the answers for the earlier recurrence relations for greater values of n. Right? So if again, we went through this last time, but I'm trying to reinforce things to make sure people get it. So when I want to compute 5 factorial, right, I said 5 according to the recurrence, 5 factorial is 4 factorial times 5. That is f of n is f of n minus 1 times n. And 4 factorial, we don't have an answer right away, but it is 3 factorial times 4. Then 3 factorial is 2 factorial times 3. Then you see it keeps on going. We don't have an answer right away, but the thing is how far we can keep going to lower order terms. Can go up to this 0 factorial, and we cannot keep going further down. We cannot say f of 0 is f of minus 1 times 0, because factorial, this recurrence that you have for factorial in general, how did we write it? F of n minus 1 times n for n greater than 0. Right? So we cannot write this for n equal to 0 like this. So this is not possible. So this is a terminating condition. Now we need to have an answer for f of 0, using which you can compute the other f values for n greater than 0. So we need to define what is f of 0. If we don't define what is f of 0, we cannot continue further, because this recurrence is true for n greater than 0. So what is the recurrence for n, or what is the function value for n equal to 0? So there's no recurrence. It's called the basic or terminating condition, and whatever is the value for f of 0, we need to define that. And for a factorial, it is f of 0 is 1. So once we know that f of 0 is 1, we can substitute f of 0 as 1, and 1 times 1 is 2, and 1 times 1 is 1, and then substitute back for f of 1 as 1, and 1 times 2 is 2, and then substitute f of 2 is 2 and get f of 3 to be 6, and so on. We build back. So that's the idea behind recurrence. So you see, the terminating condition is very important, how low we can go. Alright, so in this case we have x of n is x of n minus 1 plus phi. So that's something given to you as a recurrence relation. So we need to solve for that and find x of n as some theta of n. So what is that function? So this is in the linear format, so we can keep reducing to lower order terms linearly. So x of n minus 1 according to this recurrence can be written as, so replace n with n minus 1. We're going to get n minus 1 minus 1 inside, so it's x of n minus 2 plus phi. That is simply for x of n minus 1. It's x of n minus 2 plus phi, plus this phi, which is written outside the square bracket. So x of n is x of n minus 2 plus phi plus phi. Instead of writing 10, I'm going to write it as 2 times phi, and you'll quickly see the reason why I wrote like that. So right now x of n is x of n minus 2 plus phi times 2, or 2 times phi mean the same. Now let us go one term further down. So replace n with n minus 2 here. we're going to get x of n minus 2 is x of n minus 2 minus 1, which is x of n minus 3 plus 5. So that is for x of n minus 2 is x of n minus 3 plus 5 plus this 5 times 2. So x of n is x of n minus 3 plus this is 5 plus again 5 times 2, that is same as saying 5 times 3. Okay, so that is like 10 plus 5, 15, so that is 5 times 3. Now you see a trend here. If it is 1 inside x of n minus 1, we have kind of like 5 times 1. If we have x of n minus 2, we have 5 times 2. If it is x of n minus 3, we have 5 times 3. So this will help us to come up with a general relation. X of n is x of n minus I plus 5 times I. Okay, and now we can keep going until all the way to this terminating condition. So that means for until what value of I at most we can go write this recurrence relation. So for solve for I, so n minus I, put n minus I equals what is inside x of in the terminating condition, we have 1. So that means I equals, if you rearrange this, I equal to n minus 1. So if you replace I with n minus 1 in this general recurrence relation, you will have x of n is x of n minus 1. So n minus 1 is going to be simply 1. See, that's why we went all the way up to this and said n minus I equal to 1. So we got now x of 1 plus 5 times n minus 1. So replacing I with n minus 1, we get x of n as x of 1 plus 5 times n minus 1. But x of 1 is 0, so it's 0 plus 5 times n minus 1. So x of n is 5 times n minus 1. Now we can write in the theta notation. So 5 times n minus 1, you can say it's 5n minus 5, and the lower order term can be discarded and it is simply 5n. And you can discard even the coefficient and simply say it is theta of n. Okay, any question on this?
No.
Okay, anybody else, any question? Okay, all right, so let's do one more. So we have here x of n is 3 times x of n minus 1 for n greater than 1, and x of 1 is 4. So let us see how to do this. So again, this has a linear trend, so we'll try to go right away. So down, x of n is 3 times x of n minus 1. So let us try to write x of n minus 1 using this recurrence. So x of n minus 1, replace n with n minus 1, is going to be 3 times x of n minus 1 minus 2. So x of n minus 1 is 3 times x of n minus 2, and we have a 3 outside, so it is 3 times times x of n minus 2. So that is 3 square times x of n minus 2. Now again we can replace n with n minus 2. That's going to be 3 x of n minus 2 is 3 times x of n minus 2 minus 1, that is x of n minus 3. And we have a 3 square outside, so it's 3 square times this 3, that's 3 cube. So x of n is 3 cube times x of n minus 3. So we already start seeing this trend. So if it is x of n minus 1, it is 3, which is 3 raised to 1. If it is x of n minus 2, it is 2, so x of n minus 3, we have a 3. So in general, x of n can be written as 3 raised to I times x of n minus I. So until what value of I, you can keep going down. This is until x of 1, right? So we have to solve for I by putting whatever is inside this x in the general recurrence with what is inside x in the basic terminating condition. So we have n minus I here equals 1. So when you solve for I, it is n minus 1. So substitute I equals n minus 1 in this general recurrence. We have x of n is 3 raised to, instead of I, it is n minus 1 times x of n minus 1, which is x of 1. So that's why we reduced all the way to x of 1. So that's going to be 3 raised to n minus 1 times x of 1 is 4. So that is 4 times 3 raised to n minus 1. So now we want to write it as in terms of n as a function. So 3 raised to n minus 1 is like 3 raised to n divided by 3. That's what is 3 raised to n minus 1. So you have 4 divided by 3 times 3 raised to n. So that's like a coefficient. 4 raised to 3 is a coefficient. So we can discard it and simply say x of n is theta of 3 raised to n. We can't simplify beyond this. We just have a function of n, but this is an exponential function and it is 3 raised to n. Okay? Any question on this problem? Okay. Alright, so let us do the other type of problem we did earlier for the number of bits. So x of n is here x of n over 3 plus 1 for n greater than 1 and x of 1 equals 1. So if you are given problems like this, so first make sure what format is this. So this is not in the linear where n equals x of n equals x of n minus 1. So this is like a division, and x of n over divided by something. So here we are dividing n by 3, and so we can solve this by substituting for n equals 3 raised to k. Okay, so where this 3 raised to k, the 3 came from this denominator here, x of n over 3. So if you notice the other problem, we had x of n over 2, so we said it is n equals 2 raised to k. So here it is n over 3, so you can say n equals 3 raised to k. If it is n over 5, we can say n equals 5 raised to k and solve the recurrence. So solve this, substitute for n 3 raised to k and come up with a reconciliation on the basis of k. Solve for that and then replace back with n. Okay, so let's do that. So x of n is 3 raised to k is x of 3 raised to k equals x of, so n is 3 raised to k, so 3 raised to k divided by 3 is 3 raised to k minus 1. So it is x of 3 raised to k minus 1 plus 1. Now I did not specify here the range for k, but we can come up with right now. So this is for n greater than 1. So we need to find, like we did earlier, for what value of k this can be true. So like I said here, n greater than 1. So 3 raised to k has to be greater than 1. So if k is 0, 3 raised to 0 will be 1, it's not greater than 1. So we have to go for k equals 1. We have 3 raised to 1 is 3 greater than 1. So that's true. So that means this recurrence is true for k greater than 0. So that means what is x of 3 raised to 0? X of 3 raised to 0 is going to be this. So 3 raised to 0 is 1. So x of 3 raised to 0 is going to be 1. So that's the terminating condition in terms of k. So we need to now solve for k. So replace k, now you see this is in the linear format, 3 raised to k, now we have 3 raised to k minus 1. So we can reduce to lower order terms. So replace k with k minus 1, we are going to have x of 3 raised to k minus 1 is x of 3 raised to k minus 1 minus 1, that is x of 3 raised to k minus 2, plus 1 for x of 3 raised to k minus 1, then plus 1 more 1. Okay, so very similar to this. So x of 3 raised to k minus 1 is x of 3 raised to k minus 1 minus 1, so that is x of 3 raised to k minus 2 plus 1. So that is x of 3 raised to k minus 1, and substitute for this in terms of 3 raised to k minus 2, we have x of 3 raised to k minus 2 plus 1, and then we have this plus 1 like this, plus 1. So that is plus 1 outside square bracket. So we can now say x of 3 raised to k is x of 3 raised to k minus 2 plus 1, that is plus 2. Now replace k with k minus 2 here, we get x of 3 raised to k minus 2 is x of 3 raised to k minus 2 minus 1, that is k x of 3 raised to k minus 3 plus 1, and then you already have plus 2, so that is plus 3. So in general we can say x of 3 raised to k is x of 3 raised to k minus I plus I. Okay, so we need to see for what value of I we can go to the terminating condition. So we can say put 3 raised to k minus I equals 1, which is 3 raised to 0, because 1 can be written as 3 raised to 0, so k minus I will be 0. That's the terminating condition. So I equals k. So put for I equals k here, we get x of 3 raised to k is x of 3 raised to k minus k plus k, and x of 3 raised to k minus k is x of 3 raised to 0, which is 1. So 1 plus k. Now k is going to be, like if I write n equals 3 raised to k, k is going to be log n to the base 3. Right, so that's the property of logarithm. So if n is 2 raised to k, we say k is log n to the base 2. So if n is 3 raised to k, we can say k is log n to the base 3. Now we won't write in terms of theta notation, so we can discard the lower order term 1, and log n to the base 3 can be simply written as log n. So x of n is theta of log n. Okay, so as you see here, it looks like if you have this recurrence, a of n is a of n over 2 plus 1, we got a of n is theta of log n, and here we have n over 3 instead of n over 2, and this still x of n is theta of log n. So what you divide by is not really a factor. Okay, so it could be x of n over 2 or x of n over 3 or x of n over 5. X of n is still going to be theta of log n. Okay. Of course, the actual math result has the base here, but again we are looking at asymptotic notation. The asymptotic means as n increases, as n grows larger, the base of the logarithm doesn't really matter. It's still is a log function of n. It's a slow growing function of n, log n. Okay. Any question? So this is very important for you to know how to solve recurrence relations like this for exam purposes. Okay, so let me stop and save the video.